Hello, my name is Richard Fowler. I'm the designer of the autonomous aerial mobility platform for quadriplegic users. It's a multimodal head control and a Boyd swarm simulation system, allowing quadriplegics to navigate a 3D space as intuitively and easily as possible. I myself broke my neck 4 years ago and am now a quadriplegic. One of the fundamental issues is accessibility to space. I have currently what I'm sat in, a wheelchair that I am able to power myself, that does give me a fair bit of independence. This headset that you see on my head has a gyroscope mapped to a drive function for the motors, which allows me to move the wheelchair through head movements. The issue here is it's a single modality in that there is no voice control. So if I want to tilt my chair back, I have to go through a series of difficult manoeuvres and things like that. So I wanted initially to design a wheelchair that had multimodal inputs to make it as easy as possible for a quadriplegic to navigate a 2D space. During the project, I had maybe what you could call an epiphany while researching flying vehicles for able-bodied people. I came to the conclusion that why should a quadriplegic be limited to the 2D plane? Why should walls, stairs and various physical obstacles be barriers to accessing space that normal people have no problem navigating? So the project developed into an aerial mobility platform rather than a simple multimodal wheelchair that goes along the ground. And this video is to explain how the system works and how it would help a quadriplegic such as myself. To explain, I have developed three main systems, a combination of software and hardware testing. So the first system is a graphical user interface with multimodal inputs, allowing a user to log in and use a system that controls that would control a wheelchair. The second part of this is a bridge which allows that graphical user interface and the inputs that are given by the quadriplegic user, that translates into actual hardware manipulation of motors and various sensors, allowing the quadriplegic to drive using either head movements or voice control. Finally, I have done a simulation in Unity of both a flying wheelchair algorithm that would allow a quadriplegic to fly through a 3D space using only head movements or voice commands. And then I have finally developed a Boyd swarm simulation system that allows for multiple mobility solutions to be mapped on the same display, essentially preventing any collisions if there are a number of aerial mobility devices in use at the same time. In my artifacts, I have submitted some Python code for a robot bridge and an aerial mobility system, and I will first take you through how to set up and implement those two programs. Yeah. This is a robot with two motors driving each of the two wheels. You will need to plug this into a monitor and plug in a keyboard and mouse into the robot. Then open a command prompt and follow the following instructions. Okay, so first you need to open up the terminal on the Raspberry Pi and type in hostname-i. That will give you the Raspberry Pi's IP address and allow you to connect your Raspberry Pi to your computer. On your computer, you will need to connect to the Raspberry Pi, so type the following command: SSH pi at, and then the IP address of the Raspberry Pi, and press enter. It will then ask you to put in a password, which I will enter now. See here, after I enter the password, enabled, so we are now connected to the Raspberry Pi. Now on the Raspberry Pi, you'll have to have this Python file saved on your Raspberry Pi in the relevant folder, but enter the command to open the Python file and make sure you put the / server at the end, as this will connect it will start the robot bridge listening for the aerial mobility system interface to begin communicating with it. So run that command and you should see waiting for platform connections. So now you run the aerial mobility system Python file on the other computer, and it will run the graphical user interface branding screen to start with. Aerial mobility platform, then you've got a loading bar here, and multimodal autonomous assistive system, Richard Fowler, Edge Hill University, and then the system should allow you to either press space to continue or simply move through to the login screen. So this interface is the part that is truly multimodal. As you can see, I have a different headset, which is an infrared QUHA style mouse controller for my laptop. So if I plug a USB into my laptop and wear the headset, I can control a mouse, so I can click anywhere and interface with my computer using head movements. The second mode of input will be voice input, so I'll show you how that works. Delete all. Admin. So you can see it populated the username field with admin on a voice command, and this brings you into the graphical user interface. As you can see on the Raspberry Pi, it will also say connected, as the graphical user interface has connected with the hardware of the Raspberry Pi, and that should allow me to control the motors of the Raspberry Pi when I select a drive mode within the GUI, which I will show you now. This is the drive mode. I'm currently in the indoor simulation. If I move backwards, it moves the Python turtle, and this corresponds to actions on the Raspberry Pi. Yeah. There are three modes. There are three modes for the graphical user interface. The two-dimensional version of there's indoor mode, outdoor mode, and park mode all there. All of these can be overridden by either clicking the emergency stop, which can be reactivated by clicking on it, or I can use my voice activation by simply saying stop. And you can see the emergency stop is activated. On the right hand side here is the tools menu, where you have a dashboard which takes telemetric data from the Raspberry Pi and gives you a real-time output of things like speed and altitude should you be in flight mode. So we'll also have ultrasonic distance from obstacles and various other functionalities. There's also an admin section which allows you to add new users and disable users and delete users. Finally, there is an AI assistant. If you should have any questions about how the system works, the AI assistant can facilitate answering those questions. So that was the graphical user interface. Now, for safety reasons, I wasn't going to test the flight controller algorithm with hardware, and also it wasn't within the scope of this project to do so. So what I developed was a Unity world and a script for head control movements of a flying vehicle. So I'm going to show you next the simulation in Unity, and that will demonstrate how the system works in terms of allowing you to fly. So this is the Unity setup. If I press play here, the scooter is actually let me just maximize the screen. So this is my scooter. So I have a dead zone in the middle where if I hover it doesn't do anything. I haven't closed that down. Alright, we'll start this again. Okay, that was a demonstration of how the robot or the wheelchair will function in a 2D plane. For the flying aspects of the vehicle, I developed a simulation in Unity, allowing me to simulate the effectiveness of my aerial control system, both as a single standalone vehicle and the mapping of several vehicles at the same time. So if I show you the Unity, this is a little world I have designed, and the simple task at hand, if you see there's a scooter which is mapping the wheelchair and there's a penguin in the distance, and the trick is to navigate to the penguin in order to successfully demonstrate how the system works. So let me just make the screen bigger. So here it is. There's a dead zone in the middle. So if I stay central with my head, then there's no movement. If I want to move forwards, I go to the bottom of the screen with my mouse, basically tilting my head forward. If I want to move backwards, I move to the top of the screen, and that allows me to reverse. If I go left, it goes left. If I turn to the right, it goes right. Now that's pretty intuitive in terms of forward, backwards and sideways movement, but the question remains, how would a quadriplegic do upwards and downwards movements? So the way it's done is a little flick of the mouse. If I start in the middle of the screen and do a flick, I rise. A flick, I rise. A flick up, I fall. Flick, flick, rise, rise, flick, fall. So as you can see, I can fly. So one day this will map across to a drone, and let's see how easy it is to get to the penguin. Here we go, and up, down, there we go, we're at the penguin, and that's it. So that demonstrates the capability of using a head movement to fly a aerial mobility vehicle. The question remains, what would happen if there were multiple vehicles? How would you avoid it? So what I've developed is this Boyd system. So if I run this, so in order to run this, you click on aerial mobility up here, which is a new tab that has been put in the Unity toolbar. Click on build scene, and then you build it, and then press play. Again, we'll maximize this so you can see what's going on, and this is mapping 12 aerial vehicles and ensuring that none of the 12 vehicles will hit each other. I'm controlling this one here. So if any of them get too close to one another, let me just close down the... Yeah. So if any of these aerial vehicles get close to each other, this is the one that I'm controlling, you can see. If they get close to each other, they highlight in orange, and then they move away from each other automatically. So this is a base, there you go, two of them moved within range of each other and they went orange and they move away from each other. As you can see, I'm controlling this one. So the idea is that this is a traffic management control system that allows for multiple users to exist within the same space at the same time safely. Thank you for listening. I hope it's been informative and that you are able to utilize the systems I have created.